Hello everyone. In this talk, I'm going to tell you an approach to check DNS implementations for RFC compliance via automatic test generation. This is a collaboration with Ryan Beckett from Microsoft with my advisors Todd, Millstein and George Varghese at UCLA. The DNS is not something that most people talk about very often, but it is essentially the glue that holds together the internet. DNS provides a way to obtain an IP address for a service or website. For example, to say you want to check out USENIX website, you first need DNS to resolve it to an IP address. There are a lot of DNS implementations out there, understandably for various reasons. Many open source implementations and each cloud has its own DNS implementation. DNS software needs to be absolutely correct. When DNS does not work or when you get wrong response or the software is vulnerable to being attacked by malicious parties, this can have dire real world consequences. You lose connectivity worldwide. So DNS has a very unfortunate property of what we call having a large blast radius. This problem is not just theoretical either. Implementations release security advisories warning users of critical bugs in their software, asking them to update to the patched versions. There are also numerous instances of major outages that make headline news every year due to problems in the DNS. For example, the recent Slack outage was triggered by a subtle bug in how Amazon Route 53 DNS handles wildcards with DNSSEC. Slack was impacted by the bug, rolled back, and caused a big impact during their rollback. Therefore, the DNS software needs to be as bug-free as possible. Now, I am going to explain how a domain name is resolved in DNS with the help of an example. A user, say trying to access the UCLA website, sends the query ucla.edu to a local resolver. Say the resolver may be from your ISP. The resolver starts by sending the query to one of the root name servers, of which there can be many. Each server will have a file called configuration. Each server will have a configuration file called zone file, which determines how to handle each query. Let us assume the resolver sends the query non-deterministically to the second root name server. The root name server does not know the IP address of ucla.edu, but it knows how to reach edu, so it will tell this to the resolver. And the process will repeat. Eventually, the query reaches the server that has the IP address, which it returns to the resolver, which in turn returns to the user, and they can reach the web server they care about. All this may appear like a simple process, but the DNS is significantly more complex than people realize. It is essentially a very complex string rewriting system. There are two sources for the DNS complexity. The first is that there is non-determinism in the DNS. In the previous example, I just showed one execution, but there are many other nameserver combinations. The second is the complex record types. There are different kinds of rewrite records, partial rewrites like dname or complete rewrites like cname, wildcard records to match records not matched by other concrete records, and about 60 other kinds of records are defined across about 30 RFCs. To succinctly summarize DNS, I quote Jeff, who said, DNS is a lot like chess. It's a simple game in terms of the rules, but phenomenally complex in the way it can be played. So our goal in this project is to check if the DNS software is compliant with the RFCs, the DNS specifications, by finding a way to generate test cases automatically while covering the RFC behaviors. However, the major challenge is that a test case consists not just of a query, but also of a DNS nameserver configuration file, the zone file. Before we go into our approach details, I will describe what a test in DNS looks like, why is it hard to write good tests with the help of an important test that our tool generated that crashed bind one of the widely used DNS implementation. This is a test case that was completely auto-generated by the tools. Each test has two components. The first one is a zone file, which is a collection of resource records that specify how query should be handled. Records can be of many different types and have many kinds of dependencies among them. Zone files are highly structured objects with various syntactic and semantic well-formedness requirements. The second component is the query, which has a domain name and a type. If the bind server uses this zone file to answer this query, then it crashes. This simple looking test case has a lot of dependencies that need to be satisfied to crash the server. First, there should be a dname type record in the zone file. Second, that dname record should rewrite to the parent domain. Dname record basically rewrites any query ending with foo.attack.com to end with com. Third, the query type must also be dname only for the crash to happen. Finally, the more complex requirement is that the foo.attack part must repeat at least twice in the query name and it must end with com. We found that the query crashes the server as it encounters an assertion failure. Understanding the attack severity, bind call it an easily weaponizable denial of service vector. We will next look at scenarios to show how this failed assertion check can be exploited remotely by an attacker. DNS hosting services using bind's authoritative nameserver implementation are vulnerable to this attack. An attacker can upload the above zone file to the authoritative server instance through the hosting service. Generally, the hosting services host it on multiple servers for redundancy. And when the above query is requested, the server instances will crash. Since the server instance will generally be serving zone files from multiple customers, such a crash will take down zone files for all customers hosted at that nameserver. This provides a method for attackers to trivially and remotely initiate a denial of service attack against customers hosted by such a service. In the second scenario, a more serious one, which unfortunately I am not going to details, you could actually crash any public bind-based resolver. A public DNS resolver is something like 1.1.1, which resolves queries on the behalf of the users. In some estimates, bind accounts for over half of all DNS resolvers in use, which means that attackers could effectively initiate a simple DDoS attack against the numerous ISPs and public resolvers available to end users. After discovering the DNAME attack, we initiated a responsible disclosure procedure with the bind developers. Given the attack severity, they requested that we keep the issue confidential until the control release. Bind released a CVE, common vulnerabilities and exposure item, with a high severity rating and asked maintainers to update to the patched version. The attack affected all maintained bind version, which in turn affected NetApp, Ubuntu, Influbox, and Red Hat. I believe with this example, I convinced you that a test case in DNS has two components, and you need to generate both the zone file and the query together, and the query must be related to the zone file for the test to even reach the core resolution logic. Given the complex dependencies in this test case, we also want to have this test auto-generated. Before I describe our test generation approach, let us review why standard automated testers are not enough in this case. If you look at the traditional styles of automated testing, we have fuzz testing on one side. Fuzz testing is a technique in which a program is bombarded with many randomly generated inputs. Fuzz testing is scalable in general and was successful for many code bases, but it is often unable to navigate complex input requirements like zone files to generate them. As a result, fuzzers for DNS only generate queries and Y format inputs to test the DNS parsers, but not to test the query lookup logic. With fuzzing, one cannot also have any coverage guarantees. The figure shows the expected tested paths of implementation in red using fuzzing. On the other hand, we have symbolic execution of the DNS implementations. Symbolic execution is a static analysis technique that enumerates execution paths in a program and uses constraint solvers to produce an input that will take each enumerated path, so that you can cover many different program behaviors. However, in practice, it suffers from the well-known problem of path explosion that limits scalability. It also has problem with the complex data structures and program logic and will thus only typically explore a subset of possible implementation paths. Symbolic execution has coverage guarantees in theory, but not in practice due to explosion. Due to all these limitations in both the techniques, none of the existing tools that use these approaches even try to generate zone files and hence do not find RFC violations. Our approach to automated testing of DNS nameservers for RFC compliance is called SCALE, which stands for Small Scope, Constraint-driven, Automated Logical Execution. SCALE approach jointly generates zone files and the corresponding queries, does so in a way that is targeted towards covering many different RFC behaviors and is applicable to black box DNS implementations. So what was the key insight that enabled all of this? Well, if you look at the networking protocols, we notice that we have a key advantage over normal software, which is that we have a well-documented specification of what the software must do, though it is in English. So what we do is we use a DNS formal model that we developed from RFCs in our prior work, Groot, to guide the test generation here. What we have done is we created an executable version of this formal semantics of DNS, which we then symbolically execute to generate tests for DNS nameservers, each test consisting of a well-formed zone file and a query that together cause execution to explore a particular RFC behavior. This way, we cover all the possible behaviors in the logical model of RFCs, achieving a high RFC behavior coverage. We have used a scale approach as the basis for a tool called Ferret for automated testing of DNS implementations. Scale is the name we gave for the approach, and the DNS specific tool is called Ferret. Ferret generates tests in an exhaustive manner using our logical model of the RFCs in the form of pairs of zone files and user queries. Given this test, what we do then is run every name server implementation we have against the test and compare their outputs. When one or more DNS implementations disagree with others, Ferret flags this as a potential bug. The reason we do it this way is that many parts of the DNS RFCs are either unspecified or underspecified, and there is not always a correct answer. We therefore leverage the idea of differential testing commonly used in compiler testing to compare the results from the DNS implementations to one another. Next, I will explain the test generation module in detail. The way we generate the test is as follows. We start with the formal model we have from our prior work. Roughly, you can think of this model as being a very complex decision tree that the DNS goes through in order to answer a query. I am showing a highly abstracted version of the formal semantics as a decision tree for a subset of the DNS logic on the slide here. So for instance, you first look for an exact match on the top of the tree and go left or right depending on if it exists. Given this tree, we can enumerate every path to the tree. Each such path will have a set of constraints associated with it that are required of the user query and zone input in order to take that path. We solve this set of constraints using constraint solver to find inputs that meet each of these constraints. Basically, symbolic execution of the model. Now, doing this by hand looks very manual and tedious. But we have built this formal model in a modeling tool called Zen that Ryan Beckett built at MSR, which lets you formalize an executable model by writing code. It then automates this entire process, and the result is a set of inputs, or in this case test, one for each unique path in the model, and so is exhaustive. I will next tell you one of the major challenges we encountered during this process. The challenge was in generating valid zone files through Zen. Consider one path and the test generated from it. What was happening was that the generated query was valid and each of the individual records was proper but not the zone file. It was because zone files must satisfy several constraints in order to be considered well formed. For instance, there can be only one DNAME record for a domain name. So if there is a foo.com DNAME record in the zone file, there cannot be any other foo.com DNAME record in the zone file. The DNS RFCs define many such constraints to eliminate ambiguous or useless zones. Naively performing symbolic execution will produce many zones that are not well formed, and DNS implementations typically pre-process to reject ill-formed zone files, thereby failing to test the intended execution path of the query lookup logic. Our scale approach admits a natural solution to this problem. We have formalized the DNS zone validity conditions as predicates in Zen. Whenever Zen symbolic execution engine produces constraints for a particular execution path, we cojoin these predicates before Zen pass it off to an automated constraint solver. And the result is valid zone file inputs. While it is critical to be able to generate well-formed zone files, bugs can also lurk in implementation handling of ill-formed zone files. Since we have formulated validity conditions for zone files, we leverage Zen to systematically generate zone files that violate one of these conditions. Symbolic execution of this logical model is still fundamentally unscalable. There are unbounded number of possible executions paths, and they grow exponentially in the size of the zone file. We notice that DNS protocol and the implementations have a small scope property. That is, many interesting behaviors can be covered with small tests. We therefore use the length bound of 4 to generate tests, that is the maximum length of a domain name and the maximum number of records in a zone is at most 4. There were around 12,600 tests for this bound. These tests are exhaustively covering the model, that is, these are all the possible paths in the model for that bound. And at length 4, each leaf is covered by at least one test validating the small scope property. We tested 8 open source DNS nameserver implementations shown in the table using those tests. This includes popular implementations such as Bind, which is the de facto standard, as well as newer implementations like CodeDNS, which is used in Kubernetes. I am showing the confirmed bugs for each implementations and how many were critical security vulnerabilities. First of all, we found at least one bug in every single implementation we tested. Not only that, but the number of bugs was not always related to the maturity of the tool. For example, PowerDNS had only 2 bugs. In contrast, Bind is perhaps the most mature implementation, and yet we found 4 bugs, including one critical vulnerability where a user could crash the server. Some of the less mature implementations like Edifa, TrustDNS, and ManaDNS had many other issues, like with features that they don't support, but we did not include them here. Almost all the bugs in the first 5 implementations are fixed by now. During my internship last year at Amazon, I was able to test Route 53 DNS implementation using the Ferret test and found some bugs. I can't reveal the details, but I added this 12,600 test as unit test in the Route 53 DNS CI/CD pipeline. I presented this work at a DNS specific conference called DNS Org, and it was well received by the community. To summarize, Scale, the main technical challenge is to jointly generate the structured configuration files, zone files, as well as the input queries to check RFC compliance, behavior compliance. We leverage the small scope property of DNS to build an executable model of DNS resolution with symbolic execution in mind and symbolically execute it to generate high coverage tests that cover all paths in the model. Using these tests, we found 30 bugs, including 3 critical security vulnerabilities. We believe that this combination of techniques, which we call Scale, can generalize to ferret out subtle RFC compliance bugs in large implementation code bases for other networking protocols that use configurations. Ferret and the dataset are available on GitHub. Thank you, and with that, I'm happy to take questions.